Welcome, this is lecture 13 in the series. We will look at the application of Grosvenor basis to describe quotient rings and then use it as a way to determine whether a system of polynomial equations have finitely many solutions. The solution set is finite. So here is a proposition which is sort of one of the important reasons for studying one of the original motivations for studying this. Again, sorry, we are continuing with the same discussion. This is polynomial ring in sum throughout R is a polynomial ring in n variables, and this is a monomial order, and I is an ideal, and okay, so let I be an ideal. Then the set M monomial in R such that M is not in the initial ideal of I. The complement of the set of the initial ideal of I in the set of monomials is a K vector space basis of R mod I. Just let's make sure we understand what this means. Okay. Note, R is a K vector space. Okay. A basis of R for R is the set of monomials. Okay. I is a K vector subspace of R. Okay. Therefore, R mod I is a K vector space, is a quotient vector space. Okay. Now, monomials need not form a basis for I because I could be generated by non-monomial polynomials. So this may not have a basis of monomials. However, the quotient ring has a basis of monomials which comes precisely from the complement of I. Okay. So that's the proposition. So we will prove this. So we have to prove that a set is a basis for a vector space. So we have to prove two things. We have to prove that it spans and that it is linearly independent. Okay. So then, so let G be a Grosvenor basis. For I. Okay. Now let's prove both cases. Linear independence. Okay. Suppose we have some alpha I mi finite 0 mi not in the initial ideal of I for all I, and alpha I inside K. So a K linear combination of elements in this potential set, let's say it is 0. Okay. So this is 0 in R mod I. So the 0 is inside of R mod I. Okay. What does that say? This is if and only if alpha I mi. So just when we write alpha I mi is 0 inside R mod I, we mean the residue class of mi inside R mod I. But here I mean the actual monomial itself. The same sum is inside I. Okay? Which means that the initial term of the sum is divisible by in G for some G in G. Okay, that's what we mean by I mean, this we saw that this is a Grosvenor basis. Okay, so it's divisible by some G in G. Now, but what's the initial term of this? These are monomials. There is no, these are distinct monomials. There is no cancellation among them. Okay, the one that is the largest. So which means that there exists some mi not inside in I, divisible by, well, sorry, there's no contradiction yet. If alpha I is not equal to 0 for some I, okay, then, I mean, this is in fact a non-zero element, then there exists mj not inside the initial ideal of I, divisible by in G for some G in G. But this is not possible. Anything that is divisible by G, by such terms, will be inside here. So this is a contradiction. The contradiction is this assumption. Okay, this contradiction is for this. This contradiction is for this assumption. Okay, so therefore, alpha I is equal to 0 for all I, okay, which is what we wanted to prove. Okay, this proves linear independence. Now we would like to prove that the set spans the vector space. Okay. So let F be inside R, okay, and consider apply the division algorithm. Let R be equal to the remainder of F under division by G. Okay. Notice that F minus R is a sum of linear combinations of the G, so it is inside I. Okay. So in other words, F mod I is same thing as R mod I. But what's the property of R? R has a property that every term of R, such that no term of R, sorry, not every term, no term of R is divisible by in G for any G in G. Okay. So in other words, R is in the, in other words, that is, R is in the span of that set, monomials, so we can just write it, M monomial in R, M not inside in I. So therefore it spans, and hence the proof is done. Okay. So this is the property of this description of quotient rings and its relation to Grosvenor basis of I. So with this, we can use this result to prove the following theorem. Okay. This is about finiteness of the solution set throughout. So now we assume K algebraically closed because we have to use. Okay, so we don't need to assume K algebraically closed, but since we did not describe how to translate or what's the relation between arbitrary field and its algebraic closure when we work in this thing, it's better to assume algebraically closed and have a clean statement now. Okay, algebraically closed R kx1 through xn, okay, I and R ideal. Okay. Then the following are equivalent. 1. V of I, which is the solution, common solutions to all the polynomials, common zeros of all the polynomials in I, is a finite set. Okay. 2. For all I, for each of the variables, that means, there exists a non-negative integer mi, okay, non-negative integer mi, such that xi to the mi is in the initial ideal of I. So fix any monomial order, the result does not depend on the monomial order itself. Yeah. Okay. 3. For any Grosvenor basis, of I, again with respect to the given monomial order, and for all the same quantifier, meaning for each variable, it means there exists some mi non-negative integer and a gi inside G. So sorry, for a Grosvenor basis G, okay, for every pick any Grosvenor basis of I and pick any variable, then there is a non-negative integer and an element in the Grosvenor basis such that in Gi is xi to the mi. Okay. Statement 4, the K span of this set M monomial sorry, not the K span, just the set is finite. M monomial in R such that M is not inside the initial ideal of I is finite. And 5, the dimension as a K vector space of R mod I is finite. Okay. So let's look at these statements just once more. So we are trying to understand when would the zero set of I be finite. That's the first statement. Second statement says something about some nice terms, powers of variables inside the initial ideal. Third is just restatement of 2, that in any Grosvenor basis there is a polynomial in which a power of a variable is the initial term, and 4 is the complement of the initial ideal in the set of monomials, and their complement is finite, and 5, dimension of this is as a K vector space is finite. Okay, so let's finish off this proof. I mean, in the proof, let's finish off the ones that we already know. Let's look at 2 and 3. 2 says there is an xi to the mi in the initial ideal, which means that in every Grosvenor basis there is an element in the basis whose leading term is xi to the mi. So that says 2 implies 3, and if 3 is true, clearly 2 is true because this initial term shows up there. Okay, so 2 if and only if 3 is from the definition of a Grosvenor basis. So this we will not reprove. So that's okay. So this is it. Okay. What about 4 and 5? So that's the previous proposition. This set, oh, sorry, not here. Yeah, this set is a K vector space basis for this. So this is finite if and only if this is finite dimensional. Okay. So 4 if and only if 5 is the previous proposition. Okay. So what we will prove now is 1 implies 2, 3 implies 4, and 5 implies 1. Okay. So we need to prove, we need to show, it's not, that's what we will show, and that is enough. 1 implies 2, 3 implies 4, and 5 implies 1. Okay, so that's what is left. Okay, or some if you prove these statements, everything will be done. Okay, so let's prove 1 implies 2. Okay, so Vi is a finite set. Okay, so fix an I between 1 and n, and let Ai inside K be the values of the ith coordinate of the points in V of I. Okay, so just project V of I to the ith coordinate and just pick out those values, the image of that thing. So Ai is a finite set. Okay. Define the polynomial Fi of xi, define it to be the product of xi minus a inside Ai. Okay. Notice that Fi is inside, Fi vanishes at everywhere inside I. Okay. Note that the ith coordinate of any point in Vi will be from Ai, so it would vanish, so that Fi is inside I of Vi. Okay. This is the radical of I that we proved. Okay. So what does that now mean? It means now that Fi to some Ki is inside I for some Ki. But what does Fi to the Ki look like? So the initial term of Fi to the Ki is, let's quickly look. So the degree of Fi is the cardinality of Ai, and then raised to the Ki would be xi to the cardinality of Ai times Ki. And this is inside in I. And this is true for every I. Okay, so this proves that 1 implies 2. Okay, we already observed 2 implies 3. Now let's prove 3 implies 4. Okay. So notice that x1 to the a1, so an arbitrary monomial, xn to the an, belongs to, doesn't belong to I. So for each I, xi to the mi divides is in the initial ideal, is not in the initial ideal. Okay. Okay. If and only if for the ith exponent is divisible by mi, then it is in the initial ideal, because xi to the mi is in the initial ideal. So this is true if and only if ai, of course it is greater than or equal to 0, and is strictly less than mi for all I, which now implies that the complement of the set is finite. M not inside in I is finite. There are only finitely many exponents satisfying this condition. Okay, so this is finite. Okay, so now we come to the last part, which is 5 implies 1. Okay. Let's look at some fix some I. Let's look at 1, x1, xi square, and so on. Okay. So consider the set, a subset of monomials inside R. Okay. These give a linearly dependent set in R mod I, because R mod I is finite dimensional. This is countable. So if you take the images inside R mod I, inside R these are linearly independent, but if you take the images inside R mod I, then because R mod I is finite dimensional, there must be a linear relation among them. So in other words, there exists some fi in xi in one variable, such that fi of xi is inside I. Okay. This is true for every I. Okay. So true for every I. Okay. So therefore, I contains the ideal generated by f1 x1, f2 x2, and fn xn. Okay. Now, if some point in Kn has to satisfy all of these things, the first coordinate can only take finitely many values depending on this condition, finitely many values depending on this condition for the second coordinate, and so on. So if A is inside V of I, let's say A is A1 through An, then fi of ai is 0, which means that ai has to come from a finite collection, and therefore V of I is finite. Okay. The point is that V of this ideal is a finite set. Therefore, any ideal containing it also will be a finite set. Okay. So this is an useful application of the things that we discussed so far for this problem about determining if there are finitely many solutions. Okay. So now let's look at these things in Macaulay. So again, this is ignore this first line with some 2% in Macaulay. It just says that we are running some Macaulay code. Okay, so we are defining a polynomial ring. So I have changed, so far I've been more or less using Q or to decide, but once, at least in the earlier example, we saw that if you switch from G-Lex to Lex, the complexity of computing a Grosvenor basis goes up substantially. So I've used a small field to do this calculation, okay, to illustrate this calculation. So here is a polynomial ring with G-Lex order. Actually, it's the same polynomials that we chose earlier. Okay, we compute the Grosvenor basis. Okay, so we have, so here there's so this is again, the offset line is the code that is run, and the line that comes from the left, it's the full width line is the output. So it computes, I asked for the generators of the Grosvenor basis. Okay. So it gave this and this one. And we can quickly check that the initial ideal contains powers of the variables. I mean, we can do that just by directly looking at here itself. Initial term is y cube, initial term is x square, initial term is z to the 6. So all variables have their powers in the initial ideal, which we see just by looking at here itself. And okay, so this tells us that this V of I is finite in this case. Okay. Of course, we won't probably ask for it over Z mod 11, but we can only discuss it over its algebraic closure, but that's okay. Computation is done in over Z mod 11 itself. Okay, so therefore I contains polynomials f, g, there's a polynomial on x, this was what the theorem said, there's a polynomial that involves just x, there's a polynomial that involves just y, there's a polynomial that involves only z. Okay, so in principle, to find the solutions, we could just solve these one variable equations, and then so we get some finite set, and in that finite set we can explicitly check whether which of these satisfy these polynomials. Okay. Remember, these are mixed. There's a y x term, there's all variables here, there's a mixture x squared y squared term. So these don't fit this description, but if we can find these three polynomials, then we can just find the superset from which the solutions will come. The superset itself will be finite, and then one can then just check against each one of these things which of them are actually solutions and which of them are not. So, okay, so this is theoretically possible, I mean, okay, but it is somewhat tedious because it's not easy to identify such single variable polynomials, and we will see this in the next lecture, which has to do with something about elimination. Okay, so we will do this. Okay, so elimination will be discussed in the next lecture, but let's. Okay, but the unfortunate part is we have to use lex instead of glex, and it means that the computation can get really big, as we saw in the last lecture. Okay, so that's what we're doing here. We just change the order to lex, same ideal, and we asked for its. So we have seen similar example. Suddenly, in much higher degree and much higher, larger number, I mean more elements in the Grosvenor basis. So this is again similar example. We compute the Grosvenor basis of I, then we compute the Grosvenor basis of I, and then we take ask for the leading term. So it gives this output. So this is just the initial ideal. Already, I mean, we see that there are 7 terms inside here, and there's one of degree 79. Okay, so let's try to understand what it says. So there is a polynomial f3 in the ideal, with in f3 equals z to the 79. But if you have an initial term, if you have a polynomial in lex order whose initial term is z to the 79 or power of z, then it cannot involve y and x. So it must be a polynomial in z alone. There is an f2 with initial term y to the 4 here. Okay. So it must be a polynomial in just y and z. Okay, so we first can solve for this one. Then for each values of the solution, C1 through C79. So there might be repetitions. I mean, these are algorithmic aspects that one should worry about. One has to actually compute, but at least let's have an idea of how it can be done. So for each I, we can substitute Ci inside here and solve for f2 of y comma Ci. Okay. So this will give us the variety of f2 comma f3. So instead of finding the single variable polynomials, we are doing like Gaussian elimination. We first solve for the last variable, and then the next one, and then the next one. Okay. So for each b comma c in v of f2, f3, find zeros of g, x, b, c, as g takes the values in the generators. Okay. So here is just a little bit more introduction to Macaulay. So how would we know, how would we pick out among the elements of the Grosvenor basis, how would we pick out those which involve only z, or those which involve only y and z? I mean, how do we ask Macaulay to pick it out for us? Of course, if it's written, we can glance at it and then hopefully we can pick it, but that is a little tedious. So the observation is that f is a polynomial in z if and only if in f is a power of z, and that is true if and only if in f is less than y. Okay. So that's what we have asked here. So this is something called select command. Okay, and the exercise is open a Macaulay session and read the select command, help for it, and understand how it is done. Okay, that's the exercise. So I ask, it's probably clear from the context. Consider the function which takes m to the Boolean value m. So this is a monomial. I am already using that inside here. So m less than y. okay, m less than y, and I'm sorry, actually there is a typo. It should have been in m less than y, but in m is the largest, so every term is less than y. So to be correct, I should have written lead term of m is less than y. Similarly, lead, okay. So I'm giving a function from this set. So this is the Grosvenor basis. From this set, I'm asking, consider the function m goes to, or m maps to, the Boolean value true or false, depending on leading term of m is less than y. Okay. So pick out, so this command picks out all the elements in G. So G itself is a matrix, so in order to get it as a list, we have to do these commands, so please look at its help. Okay. Apply this Boolean function, Boolean valued function, and pick out the ones that are true, for which the output is true. That's what select does. Okay. And similarly here I pick the ones whose leading term is strictly less than x, which means the ones that involve y and z only. And then it will give us two lists, and then we can programmatically try to solve them. Of course, we have not discussed any way to solve single variable, very high degree polynomials. That also one has to be able to solve. Okay. I mean, if you want, like this one, there's just a single polynomial. How do we find solutions of this is a different problem which we have not discussed. Okay. So this is the end of this section about finiteness of solution set. And in the next lecture, we will use elimination. We will discuss elimination of variables, as we already saw a little bit here.